Hello and welcome to the NPTEL MOOC on Applied Electromagnetics for Engineers. In this module, we will talk about a very important topic, the topic that comes up quite often at higher frequencies, at microwave frequency or at RF frequencies. In fact, so much so that most RF designers spend about 50 to 75% of their time performing this particular function. What is this magic function that most people want to do at high frequencies? Incidentally, most people at low frequencies do not even bother about this topic. This topic is that what is called as impedance matching. What is impedance matching? Now, from your first year circuit courses, you might know very well that if I have a source with a fixed internal resistance, so whatever the resistance of that be, but if I consider a source with a fixed internal resistance, then what value of the load resistance should I connect across the source terminals such that maximum power is delivered to the source, delivered to the load. Now, this problem we know can be easily solved. You can either solve it by simple physical arguments showing that RL equal to 0 does not give you power because the voltage across RL will be equal to 0 in that case, or when RL is equal to infinity, that is short circuit or open circuited cases do not give you maximum power transfer. You will get maximum power transferred or maximum power will be dissipated across the load resistor RL when that RL is equal to Rg, where Rg is the internal resistance of the source. Now, if we consider high frequencies, we of course also not only at high frequencies, even at low frequencies, we know that the generator impedance or the generator will not necessarily always have an impedance out there. It can also have a reactive component, which means that you will be having a complex impedance as an internal impedance, something that is not accessible to you. Please remember that this model which I have put inside this dotted lines is actually something of a idealization. So, we are assuming based on our measurements that we perform at the output terminals of the source that one possible way in which the source can be modeled is to have some source amplitude and an internal resistance Zg. Of course, if you had access to Zg, then you could have had access to the power dissipated across Zg, which of course you do not have, right. So, this one that is so this is, that's why it is called as an internal impedance, and this is idealized by the fact that we have drawn dashed lines around this source. So, this is not a perfect or an ideal source, this is an imperfect or a practical source, and which has an impedance Zg which is internal to this source. Let us also assume that the source amplitude is some Vg. Of course, in the thing that we have been talking about over the last few modules, Vg happens to be a phasor, okay. But for our discussion, not really important to know what the form of Vg is. So, given a complex load Zg, right, if I were to attach to this imperfect or a practical source a variable impedance ZL, and I can change this ZL, I can of course go from ZL equal to 0 to infinity, and ZL is also complex. So, I can change both the real part of ZL as well as the imaginary part of ZL, and the question now becomes what value of ZL that I should choose in order to maximize the power delivered across ZL. So, power delivered or power transferred to ZL, the complex load, will be maximum. So, I can deliver maximum power to the load only when ZL is equal to Zg complex conjugate. What does that mean in terms of real and imaginary components? ZL, if you were to write this as RL plus JXL, where RL is the real part or the resistive part of the load and XL is the reactive part of the load, then this must be equal to Rg minus JXg, okay. So, clearly telling you that RL must be equal to Rg. This is not very surprising because this is the same case that you are going to obtain when the load as well as the internal resistance are both real quantities. That is, if both Zg and ZL consist only of resistances, then we know that maximum power can be delivered across the load or transferred to the load when RL is equal to Rg. In terms of the reactances, when the load becomes complex, then XL must be equal to minus Xg. So, if the source has a reactance which is capacitive in nature, then you need to connect at the load side an inductive reactance so that this inductive reactance can tune out the capacitor and thereby cancel the reactances of both the internal resistance as well as the load, leaving only the real or resistive cases behind. When we do this and when we take RL is equal to Rg and XL equal to minus Xg, how much power is actually delivered across the load? Please remember that if I have a load which is complex, then the power will be delivered only to the resistive part of the complex load, because we know ideal capacitors or inductors do not dissipate energy. So when you have a complex load, it is only across the real part of ZL or RL which will actually dissipate the power. Okay. So if you substitute the conditions of RL equal to Rg and XL equal to minus Xg, calculate what is the current and what is the voltage across this load. Okay. Current through the loop is the load, is the current IL, and voltage across the load is VL, and if you calculate what is the power that is actually delivered to this, you will see that the power delivered will be half of maximum power that is available from the source. What is the, so let me write this as, so power delivered under the max condition or the maximum power delivered, okay, when Zg is not equal to 0 is equal to half the power that is available. What is the meaning of half the power available? Well, this quantity available power in our definition is a slight of a idealization. Why is that so? Supposing I had the same voltage source with Vg as the amplitude, and by some miracle of nature the internal impedance was equal to 0. So Zg in this particular case was equal to 0. Now if I ask you what is the load impedance that we need to connect such that I obtain maximum power, then most of you would try to tell me that this the result should be RL equal to 0 and there should not be any complex part to this because Zg is already equal to 0. But clearly RL equal to 0 is not the correct answer, simply because connecting RL equal to 0 short circuits the load terminals and you might get maximum current, but the voltage across a short circuit will be equal to 0 and therefore no power will be dissipated. So clearly this is not the condition. So this is where it is important to realize what is the maximum power transfer concept is telling you. Maximum power concept when Zg conjugate is equal to ZL applies only when Zg is not equal to 0 and usually fixed. So for a fixed source impedance, the load impedance must be conjugate of the source impedance in order to give you maximum power across the load. Okay. So as I was saying, by some miracle, if the internal impedance were to drop to 0 or internal impedance is equal to 0, in that case no matter what load you connect, you will always end up having the power dissipated, right. So and that would actually give you the maximum power that can be extracted out of the source. Of course this source is an ideal source here simply because Zg is equal to 0. This is more of a practical source, okay. And when you look at the power that is dissipated in the ideal case, so here when Zg is equal to 0, the ideal load that I would like to connect would be any value of the load RL. For now if I just take the same value of RL in both cases, okay, I can do so because load is under my control, I am varying the load, I can take whatever value of RL I want, and if I fix the value of RL to be the same for the imperfect or the practical case and the same for the ideal case, I do obtain a certain power. What would be the power that I obtain in the ideal case? I will obtain Vg square divided by 2RL. The factor of half is because I am assuming Vg to be the peak amplitude, and as you know the power would actually be given in terms of the RMS value. So in order, or you need to know the RMS value of the voltage, which is given by Vg by square root of 2. So RMS voltage square divided by RL will give you the power. So this is what I would call as the power that is available. When you actually look at the practical scenario, when Zg is not equal to 0, you can show that the power that is delivered, which would be the maximum power that would be delivered under the condition that the source impedance is 0, is only Vg square divided by 4RL. Okay. So you can see that when you have this scenario, you are only able to get about 50% of the efficiency than you would have obtained. Okay. So you are able to get only 50% efficiency simply because Zg is not equal to 0. Okay. Regardless of the fact, what is important to take away from the last 10 minutes is that when I have a source impedance which is non-zero and fixed of a practical voltage source, then maximum power can be extracted or maximum power can be delivered to the load, provided the load impedance will be the complex conjugate of the source impedance. While this theorem is very nice to talk about and do all these simple calculations, it fails to address an important topic. That important topic is, in practice you have a practical source, okay, with some internal impedance, and you have a load which is usually not of your choice also. For example, if I buy a Samsung television or some other television, the corresponding load that the electronic circuit sees when I connect a cable would be actually fixed, right. I can change the source. Of course, source has its own internal impedance, and in the more older cases where you had an antenna, you could buy one antenna and replace one antenna from another antenna, and in that process the loads would not be exactly the same, the source impedances would not be exactly the same. So, this minor mismatches would actually mean that you are most of the times not delivering maximum power to the load. Okay. So, something has to be done in order to maximize the power that is delivered. This problem becomes even more acute when you are designing your own amplifiers, especially at high frequencies. The problem at high frequencies is that in a low frequency condition you might write a simple BJT transistor or rather BJT amplifier. You will have some base resistance and some voltage which is what you are amplifying, and then there will be some collector resistance across which you are taking the output, right. So, this is the VCC for this one, and this is the equivalent base resistance that I am writing. Okay. So, for a simple BJT amplifier like this, you do not really worry about impedance mismatch. In fact, what you want is, in order to maximize the voltage that is given to the circuit or delivered to the circuit at the output, you do not even aim for a maximum power, you aim for maximum voltage, right. So, if I replace this transistor with its equivalent circuit with a little bit of an idealization, then I know that the condition that I need to have in order to maximize. So, if I think of this as a simple amplifier, then I know that the input impedance of the amplifier to which I am now connecting the equivalent source and the voltage to which I am amplifying. So, this is my input voltage. You can think of this as a practical voltage that we are connecting, right. And then there will be some voltage gain, let us call that voltage gain as some AV times Vs, where Vs would be the voltage developed across R in, and then you will have some output impedance of the amplifier at R0. To this you will connect the load RL, right, and your goal is not to actually maximize the power transfer, because if that was your condition, you would have tried making R in is equal to R equivalent, but in practice you do not do this. What is in fact required is that R in must be much larger than R equivalent. Ideally, R in must be open circuited. So, when R in is open circuited, you have Vs equal to V in, and when R0 is equal to 0. So, in the ideal case, R0 must be very small compared to the load that you are connecting. So, in an ideal case of R0 equal to short circuit or equal to 0, you will see that the voltage across the load that you connect will be maximum, and it would be something like AV times V in, where AV is the voltage gain, right. So, you have deliberately chosen to ignore maximum power transfer theorem and actually make a mismatch. Your efficiency might improve, okay, but your power would not be the same as that is. I mean, when I say efficiency, I mean the voltage efficiency, okay, not the power efficiency. So, what is going on? I mean, why is it that low frequency people do not talk of impedance matching, whereas high frequency and RF circuit designers are always talking of impedance matching? Okay. The reason is, in the low frequency phenomenon or low frequency case, this lead which you have connected, to which you are going to connect a load resistance RL, this lead can be considered to be a wire. Okay. Similarly, the lead that goes from the equivalent resistance or the voltage source that you have considered all the way to the base of the transistor, this can also be considered to be a wire. The ground to this actual chassis ground or whatever the analog ground that you are considering, this can also be considered as a wire which connects the emitter terminal of the transistor all the way to the ground. So, this could also be a wire, this would also be a wire, everything can be considered to be a wire, and when it is a wire, it is a low frequency wire, which means it is not a transmission line. So, if what is the point of having a non-transmission line wire? If the wire is just a wire, please remember the voltage at one point of the wire will be the same as the other point of at the other point of the wire. Okay. So, because of this case, there is, and because of the large voltage gains that are involved, typical values of AV will be for a stage would be about 200 volt per volt or more than that. So, you are rarely bothered about the loss of power that actually comes because of the finite length of the wires. So, there is an issue of power, but you are not really thinking of maximizing the power because your voltage gains are so high that you can afford to lose some power. Okay. If you do the full power calculations, you will see that under this ideal conditions you will not actually achieve maximum power, but that is alright because your goal is to go only to the maximum voltage or your efficiency for the voltage, not really for the power. But unfortunately, when you go to high frequencies, right, all these lines which I drew and then happily called them as wires are no longer wires, they are all transmission lines. Okay. You see this thick line that I am using, okay, to indicate that these are all transmission lines. Okay. So, these transmission lines will, what is the property of a transmission line? You might think that you have connected a certain load here, okay, of some RL value, but unfortunately what you have connected to the collector terminal is not really a wire but a transmission line. Okay. So, what happens here is that the impedance seen looking at this point will not be equal to RL, but it could be some transformation, right. So, some RL that has been transformed because of the transmission line effect. So, it is the same at every point. So, whatever the impedance that you see here will not be the same as the impedance that you expect to see at this point. So, the impedance seen after a transmission line effect is the transformed impedance, and when there is a transformed impedance and if you do not control, if you do not know what is the impedances, then you will essentially end up having reflections at every point. Okay. What will these reflections do? They will create standing waves, and what will the effect of standing waves? They will actually not allow maximum power to be transferred. So, there is some power that these reflected voltages hold up, or the sum of the incident and reflected voltage, the standing waves hold up, which prevents maximum power to be delivered. And at RF frequencies, power is a very precious resource. You want maximum power to be transferred. If you do not transfer maximum power or do not transfer maximum energy, then you are losing out that energy in the form of a standing wave. And these standing waves can get pretty nasty. You have a transmission line, okay, and then your SWR, let us say, happens to be about 100. What it means is that the wire or the transmission line is subjected to about a voltage which is 100 times larger than the minimum voltage. Okay. If that happens, the material of which the transmission line is made out of and the structure that the transmission line exists can actually cause breakdown, or this particular large voltages can cause breakdown or voltage hotspots, right. So, there will be voltage hotspot at which the voltage is maximum, then there will be voltage minimum. Voltage minimum is reasonably okay. I mean, we are okay with the voltage minima, but this voltage maxima is pretty bad for us. These are all the hot spots that I have. Okay. Moreover, when we have a transmission line effect in the form of a connection between the load and the source, okay, then if you do not match these two ends of the circuit, so you have a generator voltage Vg with an internal impedance of Zg, and the transmission line can be modeled as a line with a characteristic impedance Z0. Let us consider an ideal lossless transmission line, and then you have a load ZL here which is connected, and if you do not match this, or if you do not perform impedance matching, what happens is that you would have created certain voltage reflections, okay, simply because ZL will not be equal to Z0, and you remember that gamma L is given by ZL minus Z0 by ZL plus Z0, right. So, you would have created a reflection here, and when this voltage comes back, we have not really talked about it, but you can easily estimate by switching this Vg onto this side and realize that if Zg is not equal to or matched to Z0 or equal to Z0, there will be one more reflection. So, in fact, these multiple reflections in the steady state is what is causing the standing waves, and these standing waves are simply, we should not have them because they create voltage hotspots, because they do not allow maximum power to be transferred. And more importantly, when you are designing a high frequency transistor amplifiers or high frequency amplifiers, there is another concept called as noise gain, okay, or optimum noise figure. So, optimum noise figure is the maximum that you can, or optimum noise figure that you can obtain for a given amplifier, and you will obtain this optimum noise figure only when your impedances are matched, okay. So, only when you are able to transfer maximum power by implementing an impedance matching network, then your noise immunity increases, because your noise figure will actually be optimized under this particular condition. So, what exactly is this impedance matching? Well, if I go back to this transmission line circuit that we have talked about, okay, you can very well see that the impedance here on the transmission line is Z0, which is not equal to the impedance of the load ZL. So, in that case what you do is you put up an extra circuit, okay, which is usually composed of lossless materials. This network is called as a matching network, okay. The objective of the matching network is that if you look from the matching network point of view from left to right at this plane, this impedance seen looking into this matching network will be equal to Z0, okay. So, what is the importance of this? When Z0 encounters Z0, when the transmission line encounters an impedance of Z0, clearly there will not be any reflections. Similarly, you put up one more matching network at this stage and look at the impedance seen here. Although the impedance to the left is Zg, after putting up a matching network, okay, your impedance seems to be equal to Z0. Again, when the waves reach the source end or the generator end, there will not be any reflection. So, you have actually eliminated reflections by performing what is called as Z0 matching or Z0 matching. If you go and do a little bit of a mathematics, you will also be able to find an expression for the available power. I highly recommend the excellent book called Microwave Engineering by Peter Rizzi, okay. I believe it is in the chapter 2 or chapter 3, he derives this equation for the maximum power. I mean, this is a simple derivation, you can do it in many ways. So, this I like because he derives it in a very simple manner, and he actually shows that, not the available power, sorry, he shows that the power that is delivered to the load is given by the power that is available. So, this is the maximum power that could be available, and this is given by Vg square by 4Z0. Again, this maximum power that is available is in the practical scenario, okay. So, you are connecting a transmission line and then you have a Zg, which is the internal impedance of the source, and whatever that power that you obtain while it comes to the load side on the lossless transmission line will be reduced. What are these factors which reduce? There is a mismatch at the generator and the transmission line. Then there is a mismatch at the load and the transmission line. So, 1 minus magnitude gamma L square is the fraction of the amount that is actually transmitted, because gamma L magnitude square times the incident power is actually reflected back. Similarly, 1 minus magnitude of G square is the one that is actually transmitted, or rather transmitted, the remaining part is actually reflected and goes into a standing wave thing. And in addition to these two, you will also see that because of this multiple reflection and propagation back and forth, there will be an additional case of 1 minus magnitude G and magnitude, or rather gamma L e to the power minus, and a minus sign simply because I have taken Z equal to 0 here, and therefore the source will be at Z equal to minus L. So, this would be minus J2 beta into L, this magnitude square. So, you can think of this gamma L e power minus J2 beta L as the input reflection coefficient, something that you would see at this point, okay. So, you will see that the total power that is delivered to the load is reduced from the available power by these factors. Now, observe a very important thing. Suppose gamma G is equal to 0. So, in this expression, suppose gamma G is equal to 0. What will happen to the load that is, power that is delivered to the load? This would be available power times 1 minus magnitude gamma L square. So, this is the average power that is delivered to the load, which is only less by a factor of gamma L, and you can make this equal to PA provided you make gamma L equal to 0. So, when you make gamma G equal to 0, this is the case of what we call as generator matched. Then if you match the load automatically the power that you obtain will be maximized. Okay. Now suppose you are unable to do the generator match. Okay. So gamma g is not equal to 0. So suppose gamma g is not equal to 0, in which case no matter what you do with gamma L, that is even when you make gamma L equal to 0, no reflections on the load side, you still end up having the load voltage or load power to be less than the maximum available power. So it is important not only to match something at the load side, but it is also equally important to match at the generator side in order to maximize the power that is delivered to the load. And there are various methods of doing this. Most matching networks fall into two major criteria, one called as the lumped matching networks and the other called as the distributed matching networks. The lumped matching networks utilize the lossless L and C and connect them in an appropriate fashion in order to form a matching network. At very low frequencies one can even use a transformer. For the distributed circuits or for distributed matching networks, you actually use a transmission line itself. Okay. Various combinations of transmission line, with transmission lines being open or closed, all these combinations are used. Okay. Usually lumped elements are okay until up to say 2 to 3 gigahertz. Beyond this, the dimensions that are required to realize an inductor or a capacitor become so prohibitive that you simply go to the distributed or the transmission line approach, and here you can either use an open circuited transmission line or a short circuited transmission line. You can have a discrete scenario in which you actually have an open circuited stub propagating through the is varied along the transmission line, or it could be a printed circuit board in which you create a microstrip line. The microstrip line will act like a transmission line. That microstrip line could be either open circuited or closed circuit or short circuited by drilling a wire and connecting it to a ground plane. Okay, so these are the major types of matching networks. When you design a matching network, what are the qualities that you are looking for? Your matching network should be simple in the sense that the network should be easily tunable and it should not be too complicated to implement. So you can have very unphysical effects or unphysical values that cannot be implemented, and your matching network would be pretty bad. Okay. The matching network could be either narrowband or broadband. If you are designing filters, you try a narrowband matching network. If you are designing amplifiers, broadband amplifiers, then you want a broadband amplifiers. You can also need or you also want narrowband but multi-band simultaneously. So you want one matching network at 2.4, the same matching network should also match at 4.8 at another frequency and so on. Okay, so these are multi-band networks. And when you design these matching networks, it's also important that you minimize the loss by the matching network itself. Why is the loss present? Because no matter what ideal components you take, but in practice those components have some amount of loss, and your goal as a matching network designer would be to minimize this. Finally, matching networks should not cost much, they should be relatively cheaper or inexpensive so that they do not become the major cost component in your microwave circuit. We will see how to perform this matching network or how to design these matching networks in the next module. Until then, thank you very much.